Okay, students, let's check on to the next question. Check whether the system described by the input-output relationship y of n equal to x square of n is time invariant. The question is very simple. Given a system describing its input-output relationship as y of n equal to x square of n, and we need to check whether the system is time invariant or not. Time invariant or time variant. This is our aim. So this is the procedure to find whether a system given by a definite input-output relationship is time invariant or not. First you shift the input. First you shift the input by some time unit n0. Okay, and keep the result in some equation number 1. Then look upon the output and shift the output by the same n0, and observe the second equation. If both equations are same, then you can definitely say the system is time invariant. Okay, otherwise it is time variant. So let us first shift the input by n0 unit. Okay, so let me denote that output. Okay, the particular output by y1 of n or y dash of n. Okay, I am getting y dash of n as output when I shift the input by n0 unit. Okay, I'm shifting the input alone. So y dash of n equal to x square of n minus n0. This could be my equation number 1, obtained by shifting the input alone. Now I'm taking the equation to shift the output by the same n0 unit. Therefore I can write it as y of n minus n0 equal to, what happens to the RHS? Since this is a function, since this equation is a function, if I am changing n to n minus n0, then wherever is n in the RHS, I have to change it to n minus n0. Okay, so you will end up with this equation, x square n minus n0. Okay, so that is the equation I have obtained when I have shifted output by the same n0 units. So I am indicating it by equation number 2. Now observe equation number 1 and equation number 2. Both have the same RHS. Equation number 1 and 2 are same, indicating that this system is time invariant. Time invariant. That's the answer. Okay, let's do the next problem. Determine the power and energy of the following signals. Classify them as energy or power signals. Given the first question as x of t is equal to a sine omega t. Okay, so at a single glance, you may be able to arrive at the conclusion that this signal is a periodic signal because it is a sinusoidal one. Okay, so all periodic signals are power signals. So we will start with calculating the power of the signal. And what is the expression for the power of a signal, periodic signal? It is calculated over one time period. So 1 by time period, integral over 0 to time period, that time period, mod x of t square. This is a real signal, so x of t square or x square of t dt. Okay, right. So that is equal to 1 by time period, integral over 0 to t. Here x of t is a into sine omega t, so x square of t becomes a square into sine square omega t dt. Okay, that becomes equal to, a square is a constant, so I can take it outside the integral, a square by t, integral 0 o t, sine square omega t can be written using trigonometric identities as 1 minus cos 2 omega t whole by 2 dt. Okay, that is equal to, again I can take 2 outside the integral, so a square by 2t into integral 0 to t dt minus integral 0 to t cos 2 omega t dt. Okay, that becomes a square by 2t into integral dt is t minus integral cos 2 omega t dt is sine 2 omega t whole by 2 omega. This is both are under the same limits, so 0 to t. Now let us apply upper limit and lower limit. becomes a square by 2t into, applying the upper limit, t minus sine 2 omega capital T by 2 omega. We are applying the upper limit capital T. Okay, minus, applying the lower limit, you get t as 0 plus sine 0 by 2 omega is 0. Okay. Now, this is equal to a square by 2t into t minus, what is sine 2 omega t by 2 pi? T is actually here, t is equal to 2 pi by angular frequency. What is the angular frequency of the input signal? You can scroll down and check it as, the coefficient of t inside the sine will be the angular frequency. So omega is the angular frequency. Okay, omega is the angular frequency. So t equal to 2 pi by omega. So t equal to 2 pi by omega. Okay, I can substitute sine 2 omega into t is 2 pi by omega whole divided by 2 omega. Okay, then this becomes equal to a square by 2t into t minus, I can cancel omega and omega, so this becomes sine 4 pi, right? This term is sine 4 pi. Sine 4 pi is always 0. Okay, so this entire term becomes 0. So what you're left with is t itself. Okay, and finally t and t cancel to give you the power as a square by 2. Okay, so this is the finite value. So the signal is a power signal. You can calculate energy also. If you calculate energy of the signal, you will end up with an infinite value. Okay, let us do that. E equal to integral minus infinity to infinity a square sine square omega t will give you a square into integral minus infinity to infinity. Or you don't need to perform this integral, because what is integral minus infinity to infinity sine square omega t dt? Actually, sine omega t is the signal. Okay, roughly the signal. What is sine square omega t? Sine square omega t means you are squaring. If this is within a n minus a, sine square omega t will be like this. The negative half also will be positive, right, with amplitude a square. Okay, now integral over minus infinity to infinity sine square omega t means you are finding the effective area under this entire graph. And this signal, it's a periodic signal. It extends from minus infinity to infinity. So the area covered by the signal or this graph is definitely infinity. So this answer is tending to infinity. So we have got the power of the signal as a square by 2, which is a finite value, and energy as infinity. So the signal is definitely power signal. Okay, let's continue with the question B. Given signal as a discrete time unit step signal x of n equal to u of n. So is the signal a periodic signal? No. What can be our inference if it is, whether it is power signal or energy signal? We can't be sure. Okay, actually this type of signal, x of n equal to u of n is a discrete time a bounded signal, right? Infinite signal, infinite duration, but bounded signal. Bounded because its amplitude is always 1. It never goes to infinity. Only its time of duration goes to infinity. Okay, so such signals which are bounded in amplitude and infinite in duration are actually power signals. Okay, or forget it. Just let us prove it by our derivation. So let us find the energy of the signal first, or power, whatever it is, no problem. So while finding the energy, the expression is sigma n equal to minus infinity to plus infinity x of n square, which is u of n square. Okay, so sigma, you don't need to sum it from minus infinity, just started from n equal to 0 to infinity, u of n square, right? U of infinity, okay, u of n square, right? Now we can substitute various values for n. For n equal to 0, what is u of n? U of n is 1. U of n square is 1 square. Okay, 1 square. N equal to 1, same 1 square, same 1 square, and it goes to infinity. Okay, what is the addition of all these infinite number of samples, each having amplitude 1? Infinity, definitely going to infinity. Okay, so we got the energy of the signal as infinity. Okay, now let us see the power of the signal. We know the expression for power, for evaluating power for a non-periodic signal is given by P equal to limit n tends to infinity. N is the time period. Time period tends to infinity. 1 by 2n plus 1 sigma n equal to minus n to plus n x of n square. Okay, this is the expression for evaluating power for a non-periodic signal. Okay, now let us start from this equation to obtain power for u of n. Okay, sigma, there is no minus n to 0 values, right? X of n, u of n starts from 0, so minus n to 0 will be 0. So n equal to 0 to n u of n square. Okay, that is limit n tending to infinity 1 by 2n plus 1. While we evaluate or expand the summation sigma, what you will get is 1 square plus 1 square plus 1 square, etc. How many terms? Is it infinite? No, never. Is because the sigma is only from n equal to 0 to n equal to capital N. Okay, so up to 1 square, how many terms will be there? There will be n terms. No, it is not n, it is n plus 1. You have to be very careful here. There are n plus 1 terms here. Why there are n plus 1 terms? Because the summation is from 0 to n, including 0 and n, there will be n plus 1 terms. Okay, so the answer to this expression will be limit n tends to infinity 1 by 2n plus 1 into 1 plus 1 plus 1, etc. n plus 1 means there will be n plus 1 as the sum. Okay, that is equal to limit n tends to infinity n plus 1 by 2n plus 1. And as you know, if limit n tends to infinity means limit 1 by n tending to 0. Okay, so I can change it as limit 1 by n tending to 0. I'm taking n from the numerator, so 1 plus 1 by n divided by, again I'm taking n from the denominator, which will give you n into 2 plus 1 by n. Okay, we can cancel n here, which will give you limit 1 by n tending to 0, 1 plus 1 by n by 2 plus 1 by n. What is the answer to this expression? If you are giving or substituting 1 by n as 0, because 1 by n tends to 0, 1 by n as 0, the output will be, or the expression will be 1 by 2. Okay, so we have started with evaluating energy, right? Energy, we got it energy as infinity. Then we started with power and we got it as 1 by 2, which is a finite value. So what is our inference? X of n equal to u of n is definitely a power signal. Okay, power signal. So that is why I have said already that signals which are bounded and infinite in duration will be power signals. Okay, so x of n equal to u of n is a power signal. Alright, next is the theory question. Distinguish between energy and power signals. Give an example for each category. So, energy signals, under the energy signal we can have many points. The first point can be for energy signals to be called as or categorized as energy signals, they should have finite energy and their average power is 0. Okay, then energy signals are usually, or they are actually finite duration signals, and they are actually non-periodic in nature. Okay, and what is actually the expression to find out energy? Energy is, for a continuous time signal, it is integral over minus infinity plus infinity mod x of t square dt. Okay, in case of discrete time signals, energy is summation from minus infinity to plus infinity in n mod x of n square. Okay, now what is power signal? What all points can be included under the category power signals? Similar to the above, power signals are defined or categorized as power signals if they have finite power, and the energy tends to infinity, energy goes to infinite. Such signals are power signals. And usually periodic signals are power signals. But there are some other signals, as I have explained in the previous question, that signals which are non-periodic, but if the signals are bounded and infinite duration, then such signals are actually power signals. Example is u of t or u of n. These are actually power signals. Okay, because their amplitude is bounded, means amplitude is finite. Okay. Next we can express the power of average power. This is average power actually. Average power of a signal, if it is continuous time, 1 by time period, integral over 1 time period, mod x of t square dt. Okay, this is for a periodic signal, right? And in case of discrete time periodic signal, this was continuous time periodic. Okay, for discrete time periodic signal, average power is equal to 1 by n, sigma n equal to 0 to n minus 1. Summation is also in 1 time period. 0 to n minus 1 means 1 time period, mod x of n square. Okay, so these are the expressions. And the question also asks us to mention some examples for each category. So what are the examples of energy signals? Any finite duration non-periodic signal, like gate function, right? This is rect of if it is 1, and if it is from minus t by 2 to plus t by 2, this is a rect of t by t. Okay, rect of t by t is an energy signal. Then triangular signal. Okay, triangular signal as 1 minus mod t by t is a finite duration signal, which is also an energy signal. Okay, a rectangular pulse or triangular pulse, these are also energy signals. Now coming to power signals, what are the examples of power signals? Any periodic signal is a power signal. So x of t equal to sine omega t is a power signal. Y of t equal to 2 cos omega t plus pi by 2 is a power signal. Then w of t is equal to 3 plus cos omega t minus pi by 4. These are all power signals. The presence of a DC will not alter the periodicity and power of this signal. Okay, so these are all power signals. Okay, that's it. Alright, shall we move to the next question? Okay, a system has input-output relation given by y of n equal to n x of n. Determine whether the system is memoryless, causal, linear, time invariant, or stable. Okay, we have to check all these conditions for the given system y of n equal to n into x of n. Okay, first let us see whether it is memoryless or not. given y of n is equal to n into x of n. Okay, so the output depends on that instant of x of n alone. Okay, there is no dependence on x of n minus 1 or x of n plus 1 something. Okay, that means the system has no memory. Okay, so the system is memoryless. Memoryless systems are also called static systems. Systems with memory are also called dynamic systems. So this system is memoryless or static. Okay, the next is so memoryless we have checked. The next is causality. The given is expression is y of n equal to n into x of n. That indicates the input output relation of the system to be checked. So clearly the input output relation or output has no any dependence on x of n plus 1. Okay, or x of n plus 2 future values. No future values are depending, or the output is not depending on any of these future values, which says the system is causal. System is causal, practical system. Okay, next is so causality check is over. We got it as causal. Next is linearity. Right, how will you check linearity? To check linearity, we take the given input output relation representing the system. Okay, linearity holds if and only if the system possesses both homogeneity and a superposition. So if you incorporate both homogeneity and a superposition check, we can say that first, this is a procedure. This procedure can be adopted to every problem, whether to check its linearity. So first you take the input as a weighted mixture. So a1 x1 of n plus a2 x2 of n. Okay, the idea is we are taking the input itself as the weighted sum of two inputs. Okay, x1 of n and x2 of n. Okay, now what will be the output? I can indicate it as some y dash of n. Okay, y dash of n will be equal to n into our input x of n is now mixed. Okay, a1 x1 of n plus a2 x2 of n. I can rearrange it as a1 into n x1 of n plus a2 into n x2 of n. Let this be equation number 1. Okay, so what we have done is we have taken the input x of n as a mixed weighted sum of two mixtures. Okay, and now let us weight the output itself. Okay, take output as weighted sum. So I am going with a1 y1 of n. I have to find the value of a1 y1 of n plus a2 y2 of n. See, the output is also a weighted sum of two mixtures. Okay, y1 of n plus y2 of n. So what will be the value? a1 into what is y1 of n? If y of n equal to n into x of n, then I can write for a specific value y1 of n will be n into x1 of n. Okay, so a1 into y1 of n is n into x1 of n plus now this is a2 into y2 of n. So a2 into y2 of n. Instead of y2 of n, I can write n into x2 of n. Okay, so this is a1 n x1 of n plus a2 n x2 of n, which is equation number 2. Now the RHS of equation number 1 and equation number 2 are same, which tells you that this system is a linear system. Okay, so the linearity check is also over, and next is checking time invariance. Okay, it's just time invariance. Okay, and let's next check the time invariance. Time invariance. Checking time invariance of a system also has a procedure. The given system is y of n equal to n times x of n. What we do first is shift the input alone. Okay, so the obtained output is some y dash of n. Okay, so y dash of n is equal to, I can write n into, I am shifting input alone by n0 unit. Okay, n into x of n minus n0. This is equation number 1. Okay, now I am attempting to shift the output by the same n0 units. Okay, so from this equation I can write output is shifted by n0 units means y of n minus n0. So since this equation is a function, then I'm changing the argument of the function from n to n minus n0. So wherever you can see n in the RHS, you have to change it to n minus n0. So that comes to n minus n0 into x of n minus n0. That is equation number 2. Okay, equation number 1 comes from the fact that I have delayed or shifted input by n0 units, and equation number 2 comes from the idea that I have shifted the output by that same n0 units. And observe equation 1 and 2 and its RHS. Is that same? Are they same? No. So equation number 1 and 2 are having different RHS. That indicates the system is not time invariant. Not time invariant also means the system is time variant. System is time variant. Okay, that's the answer. So our time invariance check is also over, and the final one is stability. Okay, stability. So how can you say that stability is also called a Bibo stability, right? Bibo stability means if at all you're giving a bounded input, then the output of the system should also be bounded output. Okay, if at all the input is bounded, output also should be bounded. Okay, so y of n equal to n into x of n is the given input output relation. So we have to assume that x of n is bounded. Okay, when x of n is bounded, or mod x of n is a finite value, then what happened to mod y of n? Mod y of n is equal to mod n into x of n, right? What happens to, or what can you infer about the stability of this system from this equation? In a single glance, you may feel that this system is stable, but assume n tends to infinity. N is a very large number. What happens? This, your x of n is multiplied by this, right? Infinity, right? So what is this? This is not, this is not a finite value. It goes to unbounded levels, very high amplitudes. Okay, so the system is not stable. Okay, that ends this question. Okay, the next question is, a signal is given by x of t equal to 1 between minus 1 and 1 and 0 at all other times. Okay, and we are asked to sketch x of 3t plus 2, first question, then x of 2 times t minus 2, okay, and x of 2t minus 1, minus 2t minus 1. Okay, so we have already done many problems of this kind, so we can very quickly finish this question. First of all, we are given x of t. Okay, we given x of t is 1 for minus 1 to 1 and 0 otherwise. We can draw that x of t first. Okay, so x of t is 1 between minus 1 and 1. Okay, so the amplitude is 1 between t equal to minus 1 and 1. Minus 1 less than or equal to t less than or equal to 1 means between minus 1 and 1. The amplitude is 1. Okay, now this is x of t. From x of t we have to first find out x of 3t plus 2. First find out x of 3t plus 2, and there is you can clearly see that there are two operations in the signal, two time operations simultaneously. The first one is shifting operation. First, according to precedence rule, first we have to do shifting operation, then scaling by 3. Okay, first shifting by 2 to the left because it is t plus 2. Okay, so shift x of t 2 units to the left and then scale by 3. Okay, x of t shifted by 2 units to the left means this end comes to minus 2 and minus 3, and this end comes to 0 and minus 1. So the signal would look like this. Okay, so verified, the signal is this x of t plus 2 is exactly x of t shifted by 2 units to the left. Okay, and the amplitude is never changed, it is 1. Okay, now what is the next step? Obviously what we need to get is x of 3t plus 2. What we have in our hand is x of t plus 2. So scale the signal by 3 or compress the signal by a factor of 3. So okay, so how to draw x of 3t plus 2 from x of t plus 2? The amplitude at minus 3 as such goes to minus 3 by 3, which is minus 1. Okay, and the amplitude at minus 1 goes to minus 1 by 3, that is minus 1 by 3 here. So we can draw it as amplitude minus 3 goes to minus 1, and amplitude minus 1 goes to minus 1 by 3. Okay, this is minus 1 by 3, and again note that amplitude never changes, right? So this is x of 3t plus 2, which is the answer to our first question. Next we have to find out x of 2 times t minus 2. Okay, x of 2 times t minus 2, that is same as x of 2t minus 4. Okay, so if you write like this, we can directly apply precedence rule. What will be the result when we apply precedence rule? First, shift the signal by 4 units. Okay, t minus 4 means we are shifting the signal by 4 units to the right. Okay, to the right, and after that we are scaling the signal by 2. Okay, let's do this. So first I am going to shift the signal by 4 units to the right. That will give you x of t minus 4. Okay, so what happens is the signal x of t shifts to 4 units to the right. So 1 2 3 4, the signal should start at 3. Okay, I had to increase the duration. So okay, so the signal shifted by 4 units means 1 2 3 4 starts at 3. Okay, so the signal x of t minus 4 starts at 3, and this amplitude at t equal to 1 goes to 4 units shifted means goes to 1 plus 4 is 5. Okay, 1 plus 4 is 5. Okay, so this is x of t minus 4, and again you note that amplitude is unchanged, amplitude is 1. And then so we have shifted this signal to 4 units to the right. Next step is to scale this by 2 units. Scale by 2, scaling factor is 2. So what is the result of scaling by 2? Amplitude at 3 comes to 3 by 2, 1.5 here. Okay, amplitude 3 1.5, and amplitude 5 divided by 2 is 2.5, comes here. Okay, so I can draw it. Amplitude 3 is coming to 1.5, 3 by 2 1.5, and amplitude at 5 becomes possible at 5 by 2 or 2.5. Okay, this is 3 by 2, this is 5 by 2. Again amplitude is unchanged. This is x of 2t minus 4. Okay, so that is our answer to the next sub question, x of 2 times t minus 2. And the last signal to be found out is x of minus 2t minus 1. X of minus 2t minus 1. Okay, so as per precedence rule, first find out x of t minus 1, then scale it by minus 2. X of minus 2t minus 1. Okay, so the first attempt is to draw x of t minus 1. So what is x of t minus 1? X of t shifted by 1 units to the right. So it should start from 0 to 2. 1 should be shifted to 2. Minus 1 should be shifted to 0. Okay, so I can easily draw it to like this. Okay, so this is x of t minus 1. Now we have to scale it by a scaling factor of minus 2. So there is a folding involved. So I can say the amplitude at 0 occurs at 0 divided by minus 2, that is still 0. Okay, so amplitude at 0 occurs still at 0 because 0 divided by minus 2 is the scaling factor. 0 divided by minus 2 is still going to be 0. Then amplitude at 2, right? Amplitude at t equal to 2 goes to 2 divided by minus 2, which is minus 1. Okay, so there's a folding, minus 1. Okay, amplitude is never changed because this is a time operation. So I can write this as x of t minus 1. First shifting is done, then it is scaled by minus 2. So a folding is occurred, so the signal is this thing. Okay, so this is our final answer. So let us look up to the next question. Derive the condition for stability of a discrete time LTI system in terms of its impulse response. So the question asks us to derive the condition for stability in terms of impulse response for a discrete time LTI system. So first of all, let us remind what is that condition. That condition is to be stable, a discrete time LTI system should obey this condition, that modulus of its impulse response, right? Modulus of its impulse response when summated from minus infinity to infinity give you a finite value. Okay, give you a finite value, maybe equal to mx, some finite value. Okay, mx or my, whatever it is. Okay, so this is the condition. The impulse response of a discrete time LTI system should be absolutely summable. Okay, now let us attempt to derive this condition. So in an LTI system, we will start from the scratch. For an LTI system, the output of that LTI system for a given input x of n with impulse response h of n will be x of n convolution h of n. You know this. Okay, you know this. And since convolution is commutative, I can write it as h of n convolution x of n also. This is also right. Okay, and now let us expand this equation using the expression for convolution sum, which is equal to sigma k equal to minus infinity to plus infinity h of k into x of n minus k. Okay, this is y of n. And now let me take the modulus value on both sides. Modulus of y of n will be equal to sigma over k equal to minus infinity to plus infinity modulus of h of k into x of n minus k. Okay, and now I can write it as modulus of y of n is sigma over k equal to minus infinity to plus infinity. Look at this equation. This is of the form modulus of a into b. Okay, in the next step I am going to write it as modulus of a into modulus of b. Okay, if I do that, what changes will occur? This I can write as mod h of k into mod x of n minus k, but one change will occur there. This equality will not hold any further, but it will be an inequality less than or equal to. Okay, this is called a Schwarz inequality. You might have studied it in linear algebra basics. Okay, so mod y of n less than or equal to sigma k equal to minus infinity to infinity mod h of k into mod x of n minus k. Okay, now actually before proceeding to the next step, I have to mention that we are going to derive the condition for Bibo stability. Okay, Bibo stability. Bibo stability means, a bounded input should give a bounded output. This is very simple. A bounded input should give a bounded output. Then the system is stable, Bibo stable. Okay. In other words, if the input to a system is bounded, okay, if the input to a system is bounded, then the output should be bounded. That is Bibo stability. Okay, if the input at all, the input is not bounded, then it's not fair to insist that the output should be bounded. Okay, so to be fair, we are assuming the input bounded, then the output also should be bounded. That means Bibo stability. Okay, so I'm taking mod of x of n. Okay, mod of x of n, as per our assumption, it should be a finite value. Let it be mx. I'm changing it as just m. Okay, to avoid confusion. So input should be a finite value, mx. Alright, so what is mod x of n minus k? I'm shifting input by k units. Will that affect the stability or convergence? No, shifting does not alter the amplitude. So still, even if it is shifted, the amplitude becomes mx, finite value. Okay, now let us come back to this equation. Okay, here I can say that mod y of n is less than or equal to sigma over k equal to minus infinity to plus infinity mod h of k into mx, right? We have assumed that input is bounded. Okay, now I can write it as this. Gives me mod y of n less than or equal to, this mx is a constant, I can take it outside the summation, mx sigma over k equal to minus infinity to plus infinity mod h of k. Okay, and you can see that this k variable is a dummy variable. Okay, I can change it as n2, right? That implies mod y of n less than or equal to mx into sigma n equal to minus infinity to plus infinity mod h of n. Okay, now let us look at the equation very carefully. The output, LHS means output, the output is less than or equal to mx into some factor, mx multiplied by some factor. So our aim is to obtain the output as bounded given the input is bounded. Okay, and the RHS is mx multiplied by some factor. Okay, so if the LHS is bounded, then the RHS also should be bounded. Clear? Okay, in the RHS, mx is already finite. Okay, to remain this RHS as bounded, this factor also should be a finite value. Then only the RHS is bounded. Okay, then only the LHS also gets bounded, which is our required expression. Okay, required condition. Okay, so this factor should be a bounded value or finite value. That means I can write as sigma over n equal to minus infinity to plus infinity mod h of n should be finite. That is the condition derived for Bibo stability. Okay, so that is the answer to this question. You can see that we have initially derived the same condition, right? Here, the same condition as the condition for Bibo stability. Okay, so this is the answer to this question. And so dear viewers, please do not forget to subscribe our videos. That would be very great support to us. And we are extremely sorry for the background noises we are experiencing while viewing this video, because I'm doing this video under lockdown. The COVID cases are highly surging in my premises, so I cannot go out to a studio for a noise-free background and all. As soon as we are out of this COVID pandemic, I can go out to a noise-free studio and do the videos more clearly without noises. Okay, so we need your support. Like this videos, subscribe. Okay, thank you.